In this image, you will see salt and you see water here, and you see that this salt is submerged in water, and you'll notice that this green spherical circle and the purple spherical has been dissociated, or they have been separated. And this is because the water will hydrate around the chlorine and around the sodium. Having this surrounding or solvating this entire ion individually prevents them from coming back together. And so they're separated like this, and that's why a salt can dissolve in water. Anything that can dissolve in water has this effect where the water surrounds the ions or the compound so that you don't see them in a solid form anymore. So this is what we consider having something that is being very soluble. So here comes my very first definition. Soluble compounds. Soluble compounds are ionic substances that could dissolve in water because the individual ions that are separated are surrounded by the polar water molecules, and they can't come back together until you dissolve the water, right? Then if you dissolve all the water, then they can come back together. Now there's insoluble compound, and what you have learned in your past chemistry class might have been that it's the ionic substances that cannot dissolve in water. So comparing like this sodium chloride and silver chloride, you might have noticed that sodium chloride could dissociate because they're surrounded by water, whereas silver chloride, they cannot dissolve in water because they stay intact, so they are intact. The thing is, in this particular chemistry class, you'll notice that you're right, they don't, but there are a very small portion of a large of sodium chloride that can dissolve in water. So for example, say you have lots of silver chloride, so representing silver, and this is chloride, lots of it. So you got the idea, AC. So if you have a lot of these guys and then you submerge all of these guys in water, well, many of them will stay intact just as is. But then out of these many, maybe like one will separate. It's really little, but one will separate. So are they really insoluble? I guess, in some sense, they're very insoluble, but there is that one teeny tiny portion where it does provide solubility. So insoluble compounds, you can say that have low solubility, whereas a soluble compound has high solubility. So this one has high solubility, and this one has low solubility. We can always say that the insoluble compound may dissolve, but just a very little, okay? And just as a chemist, we don't say they only dissolve just a little. We just say that they have low solubility. All right, now the solubility can be expressed in an equilibrium constant, or known as the Ksp. We have learned Kc, Ka, Kb, and now we're going into Ksp. Let's kind of further go back. Kc was at where in which we had these concentration in equilibrium, and they're going in two different directions. One is going in forward and one is going in reverse direction. At equilibrium, we were able to take the product over the reactant with appropriate exponent, and that's coming from the coefficient to write the Kc equation. With the Ka, very similar, but now we've dealt with acid. So we had the hydronium ion, the conjugate base all over the acid, and same thing. It was the product over the reactant. We didn't include water because water was liquid. KB, same deal. We had the product, right, over the reactant. So KSP is going to be very similar. KSP represents the equilibrium constant for solid dissociating in water. So something that is separating in water. So for example, say you have XY solid, and the XY solid is going to separate in water in its ionic compound form. If I were to write the KSP, it's the same deal. It's the product over the reactant. But you'll notice that there is no denominator here, and you go, well, where is the reactant? And that's because the XY, the solid form is solid, okay? This XY is solid, so we don't include solid in the equilibrium constant. Just as the liquid, we did not include them in the equilibrium constant. And the only thing that we can include in the equilibrium constant are the aqueous and the gas, so hence why you don't see it. There's one more thing I'm missing here, and that would be if I were to get a different color pen, if I were to have a coefficient of m and n, then we should have to the m power and to the n power. Okay. All right. So let's do an example to kind of illustrate this. Write a KSP expression for barium sulfate. And this is a solid. So that means we take barium sulfate. What would happen if they were to dissolve in water? They would separate, and the polyatomic ion will separate with barium. So here's my barium. Here's my sulfate. What charge does sulfate carry? Charge carries -2. Barium carries a charge of +2. And these are all aqueous because they have been separated. I'm going to write solid right here and double-headed arrow to show that it's at equilibrium. Okay, so now let's write the KSP because that's what it wants to know. KSP is equal to concentration of barium and concentration of sulfate, 2 minus. And that's it. We don't put the solid on the bottom because it's a solid. We can't put that in a equilibrium concentration. All right, so let's do our learning check. Here is solid silver chromate is added to water and allowed to reach equilibrium. The concentration of silver ion in the solution is found to be 1.3 times 10 to the -4. What is KSP? Okay, so what's happening here? We're taking silver chromate, so we have silver chromate, and it's being added into the water. So we add it into the water, and at equilibrium, you have some silver in its dissociation form, and we have chromate. Oops, silver is +1 charge. Okay, this is not balanced, so we have to find the coefficient of silver, and in front of the silver should be 2, right? Since there's 2 silver here and 1 chromate, 2 silver here and 1 chromate. Since we're working with an equilibrium constant, we can bring about ICE table. That's the ICE table, and that's in molarity. Let's label all of these. This is solid, aqueous, and this is aqueous. Okay, so far so good. It says the concentration of silver ion. Silver ion is in the solution to be at 1.3 times 10 to -4. That means that silver ion here, the concentration they're giving here, is at equilibrium. So this concentration is at equilibrium. Okay, so we'll note that to the side. Let's target the ICE table. Since this is a solid, we don't need to really worry about this portion. In this area, however, is another story. Okay, let me erase that to avoid some confusion. And in the very beginning, when we just even before silver chromate has been added, do we have any silver and chromate have been separated? No, we don't have any of them separated, and that's because we just put it in water. Okay, so this is very initially it's 0. Then some change has occurred where they start to dissociate. Well, we're going to have, if there was an X here, right? If there was X amount of silver chromate that has been dissociated, it's been used up, minus X here, then that means that there's going to be positive X here, and there will be positive 2x here. Why 2? That's because you need to make sure that coefficient follows through to the 2x, okay? It means every 1 mole of silver chromate that is used, you will generate 2 silver and 1 chromate ions. Okay, now at equilibrium, we add the I and the C together. That's so 0 plus 2x is just 2x, and 0 plus x is x. Let's write the equilibrium constant for Ksp here, and that's silver to the second power and chromate, but not to the second power since it has only coefficient of 1. All right, so silver to the second power, that would be your 2x to the second power. And chromate is just x. If I were to put all this together, 2 to the second power is 4 to the second 4, and an x to the second power multiplied by x, and that would mean this is 4x to the cubed, and that's your Ksp. Now, we haven't found out we want to know the concentration of silver, okay? So we have Ksp equals 4x to the cube, so we don't know what silver is. Well, what this learning check is letting you know that the silver ion at equilibrium is 1.3 times 10 to the negative 4. Oh, what is this Ksp? It's asking for Ksp. Oh, sorry. So at equilibrium, this is going to equal 1.3 times 10 to the negative 4. That's what it's saying. All right, so we'll go ahead and solve this out for x. So we're going to divide both sides. Okay, we divide both sides by 2, and that's because we want to look for x. And when we solve this, punch it into the calculator, you'll find that it is 6.5 times 10 to the negative 5, 10 to the negative 5 is going to equal to x. Now we can put that x onto here, right here. Okay, we can put that in there in order for us to solve for the Ksp. So Ksp is equal to 4 times 6.5 times 10 to the negative 5 to the third power. So let's put that in the calculator. So we have 4 parentheses 6.5 times 10 to the negative 5, close the parentheses, and then that's to the third power. And I get 1 point, with the right sig fig, 1.1 times 10 to the negative 12 is my Ksp. Okay, And then we're going to take this and compare this value to the dissociation constant chart. And that's in your reference sheet. So take out your reference sheet. So if you see this reference sheet, you will find silver chromate, and that's in this corner. You can see the Ksp for silver chromate is 1.1 times 10 to the negative 12. So it worked out very well.